see a lot of thumbs up, so we can start. Okay, here. All right, so let's continue on to the next set of topics, which is how do I predict the direction of my branch? Right, so ธีรวัฒน์ครับมีคำถามอะไรไหมครับ
อ๋อไม่มีครับโทษทีครับ
okay. All right, so now there are multiple techniques that we can do to help and predict the direction of the branch. For example, the compiler actually do a lot of optimization in order to figure out the direction of the branch, right? This is a static technique where you compile the program and you can kind of rearrange the code that the code will become more friendly toward the hardware. For example, if the hardware always use not taken, it will try to like reorganize the code so that the if else will like trending toward not taken branch. You can also use the profile the information, right? You profile the program and kind of figure out, okay, what's the likely direction that the branch are going to do. And then there's also a runtime technique, right? For example, you can figure out, okay, if I see this PC before, and last time I take the branch, this time I'm gonna guess I'm gonna take the same branch again, right? You can use a 2-bit counter to level prediction and more, all right? So now we will first talk about BTFN, right? And followed by the runtime predictor, right? BTFN is, let's say you have a loop branch, right? You go through a loop. What's the most common results for my branch? Are we taking the loop or are we exiting the loop? So do we exit or do we keep looping? So you have a loop, right? Your code. You have the branch here. And you can take the branch or you can not take the branch. So if you have the loop, what's the most common thing? Are you taking the branch or are you not taking the branch? มีใครเขียนลูปแล้วลูปครั้งเดียว ไม่มีเนาะคือลูปมันก็จะวิ่งวนหลายๆรอบเพราะฉะนั้นสิ่งที่ common ที่สุดของไอ้ branch เราอันเนี้ยที่เป็นลูปอ่ะมันก็จะวิ่งอยู่ในลูปใช่ไหมครับ so basically the most common pattern is taking a branch so if you see that it's a backward branch so this is also a backward branch it go back in the assembly, right? This is the backward branch. So if you look at the target address and it's a backward branch, you can then take the branch, right? So that's BTFN. If it's backward branch, you take. If it's a forward branch, you don't take the branch. You basically do PC plus 4, right? So that's one technique that you can do on top of just always taking a branch, always not taking the branch. In this case, you can be more do more educated guess, which is if it branched back, you would guess that it's a loop. And if it's a loop, you're likely to take the branch again, right? So you take the branch. Otherwise, you don't take the branch and you do PC plus 4. Another possibility is to use a profile information and pragma, right? Profile mean I'm gonna like when I compile, I'll profile the application. Basically, I try to run the program quickly and like take a note of all the direction of all the brand and use this to annotate the result of your branch for the next time you actually run the code. And you can use this using pragma. Pragma is a keyword for the programmer that can provide hints. For example, if likely X, it means that the program will say that, hey, that branch is likely taken, right? It can be used for multiple purposes, including using OpenMP to run things in parallel, right? You can send a message to the system, and if it's unknown, it doesn't cause compilation error, it just do nothing, right? So that's the beauty of Pragma. And you can use this for static branch prediction, right? But if you want to be more dynamic, like you want to kind of figure this out in the runtime. When you run the code, you then, based on the code you're running, you then figure out what's the result of the branch. So the idea is, well, you can use, you can predict the branch when you run it, right? And we're gonna talk about 4 techniques. Last time prediction, 2-bit counter, 2-level prediction, and other advanced technique. So let's begin with the simplest one, last time predictor. Last time predictor, as the name suggests, right? As the name suggests, if I take the branch, the last time I see this branch, I will take the branch again. If I don't take the branch, and when I see this branch earlier, I will not take the branch. And to do this, to implement this in hardware is simple, right? So you can embed a bit, like one single bit, into your branch target buffer, right? This part is called pattern history table or branch history table. It's a history. It's a history of that program counter. It indicates the direction of that branch, right? So the state of the last time predictor is like this. If I predict taken, right? If I predict taken, basically means that if I see a branch, I would guess, hey, it's gonna take a branch. And then in reality, it's not taken. You move from predict taken to predict not taken. If you predict taking the branch, you actually taking the branch, you stay there because the last time you take a branch is the last time you see this branch, you take the branch. The same thing goes for the predict not taken state. If you actually not taking, you stay there so that the next time you see the branch again, you don't take the branch. If you predict not taken, then in reality, you take the branch and you move to predict taken. And let's go through some example. Let's say I have a code where I'm stuck in the loop and if else, and the result of the loop and if else combination is resulting in taken, 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 not taken, not taken, not taken, not taken, not taken, and taken, right? In that case, what's my prediction accuracy? If I use the last time predictor, right? And let's assume initial condition, right? Init condition is taken. I'm gonna predict taken the first time I run the program. So for the first branch, I predict correctly, right? First branch, I predict correctly. Sorry, wrong color. I predict correctly. Then I'm gonna predict because the last time I take the last time I see this branch, I take the branch. So I'm gonna predict taken again. So the next time is correct, 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 correct. Now, when I see the first not taken branch, when I see the first not taken branch, the last time I see this branch is taken. So I will predict taken, but in reality, it's not taken. So this is my first misprediction. And predict correctly, 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 and then mispredict again here, right? So over here, you get 80% accuracy. If your program is in a loop and you take until you don't take the branch here, and I think that's 5, 4, 5. So over here, you get 90% accuracy, right? What would be the pattern that would kill the performance of the last time predictor? It's going to be something like this. I take the branch, then don't take the branch, and take the branch, and don't take the branch. So you're only correct for the first time because of your luck in the initial condition. Otherwise, the rest, you're all wrong. Right? Over here, you get only 10% accuracy. So as you can see, right? As you can see, the accuracy of my last time predictor is quite okay. It's quite okay, but there can be some corner cases where it got thrown off and it performed really, really horribly, right? And we don't want that. But before we go to the better design, let's look at how we implement it, right? So to implement the last time predictor, now we're going to zoom into the branch target buffer a little bit more. So we can use the PC, the program counter, as a key to search, right? If you use the index into the table and you compare the tag will basically figure out, hey, is that PC mine? Is that row, this row here, is that row mine? If it's mine, it means that it's my PC, so that you don't have to like make a table that's too big, right? Then the pattern, the history table would be just one bit, 1 or 0. 1 means the last time I see this PC is taking the branch. 0 in there means that if I see this PC, the last time is not taken. So that 1 or 0 goes into the gate that select, right? That select whether you want to do PC plus 4 or the target address from here, right? So that's the implementation of the last time predictor. Any question มีคำถามไหมครับ All right, so if there's no more question, we can go to the next better predictor, which is the 2-bit predictor. Last time predictor is single bit, right? The next predictor would allow you to be a little bit more adaptive. So we add one more bit. This is a paper introduced in ISCA 1981. ISCA is a top conference in computer architecture. So the paper is called A Study of Branch Prediction Strategy. The observation from the paper is that if you use the last time predictor, right, it changes the predicted direction with just one different outcome, right? So the solution is we can add hysteresis to the predictor, add one more state. It means that you can keep a longer history, and you have now 2 bits to track the history so that the prediction doesn't change with one single different outcome, right? Sometimes we call this bimodal prediction, right? And the way you can implement it is you can use a technique called a saturating counter, right? Because one of the things about hardware implementation, let me go back one slide here, right? You might think that, hey, this design is too simple. It's true, it's really simple. But again, also think 1981 is a long time ago. We don't have a lot of transistors for your design. So you cannot come up with a complex solution. And here, the proposed simple solution is to add one more bit, right? So when you have 2 bits, you can have 2 states for predict taken. If you're in this state, you're going to predict that you're taking the branch. Then you have 2 more states that basically, if you are in these states, right, you are not taking the branch. Then if you're in the predict taken state and you actually take the branch, you will stay there. Otherwise, you go to the 0 and 1. We call this weakly taken. We call this strongly taken. We call this weakly not taken. And this is strongly not taken. Right? So if you're in a weakly taken state, which is the top right part, and you actually take the branch, you go back to the strongly taken because you have a better belief that, hey, I see a bunch of taken branches, so I'm gonna predict taken in a strong fashion. But if I see not taken once, I'll keep predicting taken, but I don't have the strong belief anymore. I might move to the predict not taken state if I see 2 consecutive not taken branch, right? And then if you're in the weekly not taken and you actually take the branch, you go back to the weekly taken, and the same logic stay for the predict not taken state, right? Now let's look at the performance of my predictor, right? So let's assume again, assume initial condition is at strongly taken. So if I'm in a strongly taken state, right, and I see T, N, T, I'll be correct here, correct here, correct here, correct here, correct here. I will be wrong for the first not taken, and I'll be in the weekly taken state. So I'll be wrong again right here. Then I'll be correct. This 2n would move me to the we are strongly not taken. So I'll be incorrect here as well. So you get 70% accuracy. For this pattern, you get 90% because you only wrong right here, right? And for this pattern, which used to be 10%, right? You'll be correct here, not correct here, correct here, not correct here, correct here, not correct, correct, not correct, correct, not correct. So you get 50% accuracy, right? So this is generally, this is better than using a 1-bit counter. And from the paper, it's reported at 85 to 90% accuracy, which is pretty good back in the day. In 1981, you're getting about 85 to 90% accuracy for your branch predictor, right? Using just 2 bits information in order to figure out, are we taking the branch or not, right? The question is this good enough, right? Is this good enough? The thing is, if else and for loop are everywhere, right? And you cannot fetch the address because pipeline in modern processor is really deep. It can be 30 to 40 stages, right? You cannot fetch if you don't do the prediction well enough, right? So if you fetch m instruction per cycle, because modern process, sorry, sorry about that. That was the internet. I was trying to download the video that I recorded earlier so that I can post it on YouTube. And Chulalongkorn internet is really, really bad. At least in the Wi-Fi in a medical school. So it just finished after 20 minutes. Sorry about that again. So let me do a quick recap here, right? This is actually the last slide before we go and talk about the assignment. So that was unfortunate. But is 2-bit predictor good enough for modern CPU? You don't fetch 1 instruction per cycle. You actually fetch multiple. So if you mispredict a branch, you waste n cycle per instruction fetch, and you fetch already m instructions. So you're wasting n multiplied by m per misprediction. This is a lot, right? So you want to get close to like 98 to 99% correctness in terms of branch prediction. Otherwise, the CPU would get a lot slower. So, is 2-bit predictor good enough? Back in the day, 1981, yes. Nowadays, 2021, no. 40 years later, you need a much better branch prediction. All right. So that's it for today's lecture part. We're gonna cover like the Q&A for the homework, I mean the lab, as well as the possible project proposal discussion, right? So let me stop the recording right now. And if you have